Welcome to this module on understanding mechanical system requirements. So first we have to determine what this electric drive needs to do to meet mechanical system requirements. And we'll start with systems with linear motion, and we will move on to rotary motion. And then we will define a term called moment of inertia, and we'll look at things like acceleration, speed, and position. And we'll also look at, in this module, frictional torque and torsional resonances. So let's start with a very simple case where we have an adjustable speed drive driving this mechanical load over here. And for whatever reason, this load requires this kind of a torque profile. So the speed in radians per second, it's starting from 0, goes up to 100, and then stays at 100, and then comes down to 0, stays at 0, and then it accelerates again, and this profile repeats. So, there could be, you can envision many industrial processes, for example, where such a speed profile may be needed. And electric drive should be able to meet this requirement in a very energy efficient manner here. So before we go into the details of this, let's start with systems with linear motion. Okay, so here let's say that we have a mass and we want to accelerate this mass, and so we apply this external force here, and it's being opposed by this load force over here. And so with some reference, let's define the position as x over here, and its time derivative is the velocity, and the derivative of this velocity is the acceleration. And as you can see, this acceleration would be the difference between the external force minus the load force, which is opposing it, divided by the mass over here. Okay, so mass time acceleration is the net force acting on it. Okay, so that could be summarized in this next picture over here, where here's the velocity and this is the acceleration, which is equal to the net force acting on this mass divided by the mass itself over here. So that's what is shown by these two items over here, and summarized here that acceleration is the net force acting on this mass divided by this mass over here. And the power input is from this external side is the external force times the velocity, and which could be written in this form over here. And the kinetic energy associated with this mass when it's moving at this velocity u is this 1/2 m u squared here. Now we will move on to rotating systems, which are more interesting to us because more often than not, we are dealing with rotating systems. So here we will define a term called torque, and this is force times radius if these two are perpendicular to each other. So here's you have this lever arm over here, and its length or radius, let's say, is r, and a perpendicular force perpendicular to this arm is acting over here, then the torque is really r times f. Or, if it's not perpendicular, then it's really the perpendicular component of that force. So you can see in this example here, let's say you want to keep this arm stationary at this angle theta. Okay, so what force do we have to apply when there's a mass m hanging from this arm over here? Well, there's a force, gravitational force acting on it, and the component of this f, which is opposite to the direction of this gravitational force, has to be equal to this gravitational force to keep this arm stationary. Okay, so let's move on with this torque here. So we have this rotating system that is generally that we encounter in study of this topic, and we have a motor and we have a load, and this motor is developing this electromagnetic torque, and this electromagnetic torque is being opposed by the load torque over here, T sub L. And so the difference of these two, let's call it this net torque over here, or acceleration torque, and this acceleration torque divided by the inertia of this whole system would give us the acceleration here. So we'll see in a second what this moment of inertia is, but this acceleration torque divided by this moment of inertia is the one which gives us the acceleration in this system here. So here is a very basic discussion of what this moment of inertia is. Let's take a uniform or solid cylinder and calculate what its moment of inertia is, and that is what is being done here. So the length of this cylinder is L, the radius of this is R1, but let's say that we have a differential mass at this radius R, okay, and it's moving at this some velocity v. So the force that is needed, this differential force, is this differential mass times the acceleration, which is the derivative of this velocity. All right. So now in order to find the differential torque that is needed, let us multiply both sides of this by this radius r at which we are taking this differential mass, and noting that this velocity v is omega at which the cylinder is rotating times this distance or radius r. When we plug that in to this here, we get this expression over here. Okay, and now for differential mass, what we'll say is that look at this differential mass here. It has some material density rho, and this has this arc r theta, which is this side of this differential mass, and then we have this length dr over here, and then height, I should say, and then the length dl over here. So for differential mass, we substitute this expression over here, and we get this expression over here. Now, in order to get the torque here, we have to integrate. So we will integrate this differential torque with respect to the radius, which goes from 0 to r1. This theta here goes from 0 to 2 pi, and the length goes from 0 to L, and it gives us ultimately this expression. And you can see this quantity within the brackets is the moment of inertia. So for a solid cylinder, this moment of inertia is given by this expression, which is 1/2 times the mass of the cylinder times the radius squared. So knowing that, we can see the relationship between torque, acceleration, speed, and position. So in order to accelerate this combination of motor and load, to produce this acceleration, we apply this net torque, electromagnetic torque, minus the load torque opposing it, and assuming that it's coupled to a very stiff shaft, we can add the moment of inertia of the motor as well as the load, and let's call it the sum of these two as the equivalent inertia here. And so that this net torque being applied to this net inertia would result in acceleration of this system. Okay, and this acceleration over time, as shown by this equation, would result in a change in speed. So speed initially was, let's say, at time 0, omega sub m 0, but applying this net torque and therefore this acceleration over time would result in a speed at some time t to be given by this here. And similarly, we have some initial position theta, and this speed applied here over time would give us a a new position at time t over here. So we can see that these relationships that we have in these equations can be indicated or represented by a simple block diagram over here. We are producing this electromagnetic torque by this motor, and this being opposed by this load torque, and the difference of that is this acceleration torque, which is acting on this equivalent inertia, resulting in acceleration, which integrated over time results in speed, and which integrated over time results in theta, our position. Okay. So we can also see that the power that this motor has to supply is electromagnetic torque times the speed, and the load power is the load torque times the speed over here. And at any time, the kinetic energy associated with the system is 1/2 the moment of inertia times the speed squared. Okay, maybe we can put omega sub m here in the context of this picture, but that's the kinetic energy associated with this system. The other thing we should be aware of, in our previous discussion, we ignored friction, but there's always friction, and we have to supply additional torque to overcome this frictional torque, which will tend to oppose this change in acceleration or speed and things like that. So this frictional torque is very nonlinear in general and consists of so-called stiction. There's some extra torque needed to get the things rolling, and then there's a Coulomb friction, and there's a viscous friction, which is speed dependent. And but in a simplified modeling, we can represent it by a linear straight line here. The friction torque is proportional to speed times this coefficient b, friction coefficient b here. The other thing we should be aware of is that we can have torsional resonances. So we have this motor which is coupled to load through this torque over here, not through this torque, through this shaft. And so at the motor end, the shaft torque is the electromagnetic torque that this motor is generating minus the torque it takes to accelerate this motor, right? But at the load end, this torque, the shaft torque is equal to the load torque, which has to be overcome, and the torque needed to accelerate this load over here. And the displacement at the motor end and at the load end, they are different. So theta m is the displacement angle at the motor end, and theta L is the displacement angle at the load end. And the difference of these two is this torque shaft, or shaft torque, I should say, divided by this coefficient k here. So if k is infinite, that means this shaft is infinitely stiff. Then, as you can see from this equation, that the angular displacements at both ends would be the same. And in that case, this inertia of the motor and inertia of the load can be treated as one single inertial mass. They can be combined. But if this k is not infinite and is finite, then there could be mechanical resonances. The shaft acts like a spring. And in that case, there are conditions under which we can get large oscillations. So they have to avoid it. So in summary, in this module, we have tried to understand mechanical system requirements, what torque is needed to meet, for example, the speed profile that is desired of the system. We looked at linear motion, the rotary systems. We talked about moment of inertia. We related torque to acceleration, speed, and position. And then we also looked at frictional torque and possibility that we may have torsional resonances.